So if you take a look, section 1.4, we are talking about transformations on parent functions by hand. Okay, so you want to make sure you're doing this by hand, not on the graphing calculator. If you want to then check it on the graphing calculator, go right ahead. But you want to, again, make sure that you're understanding the different pieces to this one. Today is going to be kind of the lesson. And you've seen this previously. This is where, if you remember back from Algebra 2 last year, this is like the horizontal shifts and vertical shifts and those types of things. That's what we're looking at. That's what those transformations are that we're talking about. Today is going to be kind of the refresher. Go back over that stuff, make sure you're remembering that, work on it. Tomorrow, then, I have an assignment, kind of an in-class assignment, that we'll start by going over any questions from the homework, but then I'm going to just give you time to practice in class. That way, hopefully, you can get all of the assignment done in class, so you don't have any additional homework or anything. And then Friday, we've got shortened periods anyway with homecoming and stuff, so we'll get to that point, okay, when we get there. So that's kind of the plan. The lesson today, practice it tomorrow, and then move in. Okay? So, if we take a look, here are the different functions that we're going to take a look at. Here are your parent functions. And so, if you don't want to go through and have to write all these down, if you'd rather just kind of quickly snap a picture with your iPad or your phone or something, so that you don't have to write all of them down, go right ahead, okay, and draw them all. Otherwise, this lesson is out in Canvas too. You can go out to Canvas and just bring this up if you need to. But it might be kind of handy to have this on hand, because these are the parent functions. This is your starting function right here. This is what we're going to start with. So all lines work off of this. Okay? Slopes change, y-intercepts change, things along those lines. All absolute value functions work off of that one, okay? And so on, and so on, and so on. As we go through this, a couple of things. Do me a favor now. Ian, put the phone back away. Snap the picture, and I'll put it away. Oh, gotcha, okay. So what I want you to notice is there is one point that all 5 of these have in common. Okay, and that's the point. I just talked about like the last assignment, making sure there's more specific points. When you do these graphs today, there is one specific point I want you to label. Everything else you can sketch, but there's one point I want to make sure that you have. And that is, if we take a look, if you look on your linear function here, goes through the origin. Okay? Once we go through and we start shifting that vertically, horizontally, I want to know, where does that point end up? Okay? You shift the slope, you change those types of things. Same thing with absolute value. If you notice, the vertex of your V, the absolute value, is at the origin. When you're doing the shifts and the stretches, that's the one specific point that I want to know. Where did that point end up? Okay? Same thing down here. You haven't done a lot with square root functions, I don't think, in the past. So this one might be a little bit new to you. But if you notice, the starting point is at the origin normally for the parent function. And then it's just kind of a little bit of a curve. It'll increase forever and ever, but it's just got a slight curve to it as you keep working your way through it. Quadratic functions, same thing. Vertex is at the origin. And cubic function, same thing. Goes through the origin. Okay? So that's the one specific point that I want to make sure that when you graph these, it's labeled. Okay? Everything off of that, then you can kind of sketch from there. Okay? And we'll talk about that as we move on. But that's the main idea. Okay? Notice, by the way, anybody tell me why there's a restricted domain on the square root function? Where's that coming from? Why? Versus all the rest?
Because you can have a negative.
Yeah. Because I can't have a negative. We're staying with real numbers. The domain of all the other ones is all real numbers. This one's restricted because we can't take the square root of a negative. Okay? So, let's take a look. I'm going to go to Desmos here for a second and take a look at, so here's your parent function, okay, of quadratics. Here's y equals x squared. And if you just watch, this one you don't have to do anything. Just kind of follow along. What I want you to notice is I'm going to change a, h, and k in this equation. You might recognize that from last year. Okay, it's called vertex form. But what I want you to notice is this. First thing, I'm going to go through, notice h is 0. If I just start changing that value, what does h, when you change the value of h, what does it do to the graph? It's your horizontal shift. Okay? What I want you to notice about where h is, and we'll be more specific in this second, it's inside the parentheses. It's grouped with the x. Anytime you see something that's with x, it's going to have some sort of horizontal effect on the graph. Okay? Whether it's a shift, whether it's a stretch, whether it's a reflection, there's things that are going on. But in this case, that one is shifting it. Notice, k. If I go through and I change the value of k, what effect does k have on the graph? That's your vertical shift. What I want you to notice about the graph, or about the equation, notice k is not inside the parentheses. It's not grouped with the x. Anytime there is something that is not inside or grouped with x, it's got some sort of vertical effect on the graph. Okay? In this case, the k is the vertical shift. The other part is a. And there's actually two effects that a has on the graph. If you take a look, as a gets bigger, what do we notice is happening to the graph? It's getting more narrow. As a gets, so the further away that a gets from 0, then the more narrow this gets. In effect, a is kind of like the slope. It's getting steeper, if you will. Okay, you can kind of think of it that way. The closer we get to 0, notice, the wider it gets. So and eventually, if a is 0, it becomes a constant function. But notice it's wider the closer to the 0. Further away from 0, the more narrow it gets. So that's one effect. Okay, and we'll talk about that again in a second more specifically. The other effect, what happens if a is negative? All of a sudden, a flips to a negative number, and notice the parabola is now opening down instead of up. So it also is a vertical reflection. Okay? Anytime you see negatives for that a value, a negative deals with a reflection. Anytime you're seeing a negative value. Okay? And then again, same thing on the negative side. The more negative it gets, the more narrow it gets. The closer to 0 we get, the wider it gets. Okay? So just a quick visual so you can kind of see what's going on. Now, let's formalize that. Okay? So here I've got two slides basically that kind of summarize everything. And I'll give you a heads up in advance. It's a lot of information up front. But then once you start seeing how it works, you'll get the hang of it. You'll figure it out. Okay? So don't get too overwhelmed here. So transformations, if we have some function, whatever it is, quadratic, cubic, could be whatever, some starting function. Here's the first part. Anytime you are adding or subtracting, it is a shift. Okay? Anytime you add or subtract something, you're dealing with some sort of either vertical or horizontal shift. These ones, if you notice, I called it plus c and minus c. These are vertical shifts because right here in red where it says the constant is not grouped with x. If it's inside with the x, then it's horizontal. If it's outside, then it's vertical. Okay? There's always inside is something horizontal, outside is something vertical. So that part, that's kind of like the k that we were just talking about in the quadratic one. It's the same thing. We just use c. The book uses c. That's why I have c here. Okay? So that would take my function and it would move it up or down, however many units that you have there. Vertical, you always move the same direction as the sign. So if it's plus 3 here, then it moves up 3. If it's minus 5, then you move down 5. And like I was talking about on the Desmos graph, when it had x minus h in parentheses, I said that h was inside grouped with the x. That's why it was horizontal. Here's what that looks like otherwise. Here's the horizontal movement. Okay. Notice, and again, the book uses c, so I use c in the notes here. X minus c inside the parentheses. So like the one on Desmos, that was before we squared it. Could be like an absolute value. If you're adding or subtracting something inside the absolute value, that's a horizontal shift. Could be a square root. Under the square root would be a horizontal shift. Okay? So if it is grouped with the x, it's a horizontal shift when you're adding or subtracting. And one thing you have to be aware of, notice the first part down here in red, it moves the opposite direction of the sign. Horizontal shifts always go in the opposite direction of what the equation looks like. So if I have an x plus 5, I'm actually going to take the graph and move it to the left 5. If I have an x minus 3, I'm moving the graph 3 to the right. Okay? So horizontal is always opposite. So biggest things I can try to summarize for you. Horizontal movement is when it is grouped with the x's. Vertical movement is when it is not, when it is outside. Okay, whatever function you're dealing with. Second part then is, again, horizontal movement is the opposite of what it looks like in the equation. Okay, you always go the opposite direction. Those are kind of the two biggest ones. And anytime we're adding or subtracting, we're shifting. Left, right, up, down. It's a shift if it's adding or subtracting. Okay? Some people still writing away. So that's shifts. Then we go to, there's only 3 things we're going to talk about. We're going to talk about shifts, we're going to talk about reflections, and we're going to talk about that A value where it got narrower and wider. We'll talk about, those are what are called stretches or shrinks. Okay, that's what's narrowing the graph. So there's one. Here's the second one. And I mentioned this before. Here's basically your summary right here. Anytime you see a negative, you're dealing with a reflection. And the question is whether it's a vertical reflection or whether it's a horizontal reflection. So I added vertical and horizontal because that's how so that you can kind of think of it in one way, so you don't have to try to remember one thing for shifts and something else for reflections. To try to simplify it for you, I always just think of it as horizontal versus vertical. So if you notice the negative is not grouped with the x, which means it is a vertical reflection, otherwise over the x-axis. So if that parabola is opening up, you reflect it over the x-axis, and now it's opening down. That's a vertical reflection because the negative is outside, is not grouped with the x. Okay? If that negative is grouped with the x on the inside of an absolute value or something, then you're reflecting it over the y-axis, which is a horizontal reflection. It still goes because it's with the x. You can think of it as a horizontal reflection. X-axis or y-axis, that's the difference. Okay? Any questions so far? Doing okay? All right, so then the last one is that idea of when does the graph get narrower versus wider? That's the concept. And here's the first part. I didn't put this on here yet. So just a quick heads up. You don't necessarily have to write this down. This is more just a note for you. Anytime you have reflections, it does not change the shape of the graph at all. That's what's called a rigid transformation. You learned about that way back in geometry. It's the same shape, it's the same size. It just is either opening up or down or left or right. It's just a reflection. It doesn't change anything other than that. Okay. All right, so here's the last part. So now when we take a look at a non-rigid transformation, meaning now we're going to actually distort the graph. Okay? You're either going to stretch it or shrink it. Okay? Or another word for shrink would be compress it, if you will. So when you looked when I was doing that demonstration kind of thing on Desmos, when you were looking at the parabola, notice the parabola got narrower. That's because of one of two things was going on, okay? When it gets narrow, what's actually happening is you're taking that parabola and you're stretching it vertically. So if you're taking those points and you move them up, all of a sudden it starts to narrow. If you're shrinking or compressing it, then it widens out. That's the difference between a vertical stretch versus a shrink. And I'll give you more specifics in a second. Could be kind of the same idea with a horizontal. If you take a parabola and stretch it horizontally, it widens out. If you compress it horizontally, if you're squishing it, then all of a sudden it's going to narrow. Okay? So here's how you know for each part. So here's your vertical stretch or shrink. And like I said, I know I'm throwing a lot of information at you right now. We'll get it to make sense. For now, it's kind of here's everything, and then we'll sort through it. So first part, as you're writing this down, the reason this is a vertical stretch or shrink, notice where the C is. It's outside. It's in front of the function. It's not grouped with X. That's why it's vertical. And then, like we said on the Desmos part, anything bigger than 1, the further away you get, it gets narrower. Okay? You're stretching it vertically. That's why it's narrowing. When you're between 0 and 1, you're actually compressing it. You're shrinking it down, which makes the graph wider. Why is 1 the magic number, by the way? Because notice, by the way, we're multiplying here. What happens when you multiply by 1? You get the same thing. Nothing happens. That's why bigger than 1, something happens. In this case, we stretch it. Less than 1, you're compressing it. Things are getting smaller. Okay? You're shrinking it. So I told you before, adding or subtracting, that's how you know if you have a shift. When you multiply, that's when you've got either a stretch or a shrink. Okay? When you're multiplying by some constant, you've got a stretch or a shrink. Here's the other part. Here's the horizontal portion. Oops, same idea. Let me go back for a second. Hang on. There we go. Same exact idea, except now notice where the constant is. C is inside, grouped with the X. That's why it's horizontal versus vertical. So like I said, 3 different transformations is what you're looking at. Shifts, when we're adding and subtracting. Stretches or shrinks, when we're multiplying. And reflections, when we've got a negative. Those 3 things. That's what happens to a graph. You move it left or right, you stretch it or you shrink it, and then sometimes you reflect it. Okay. Like I said, a lot of information. Now let's try to start making it make some sense as you can see it in practice here. Okay? All right, example number 1. Here we go. I gave you 3 different functions so that we can always start with a parent function and then see what happens to that parent function. Okay, what's the difference? And again, the one point I need you to, when you're graphing this, is that vertex. Okay, the point that normally would be at the origin. Where does it go based on the different numbers? Okay, so first one, is your parent function, y equals x squared. We can kind of just sketch that in right away. That looks something like that. Okay, there's my starting point. There's the origin right there, the vertex. Now, for g of x, notice it's the quantity x plus 4 squared. So the question is, what does that plus 4 do to the graph? And that's really the main idea, by the way, of this whole lesson. When you start changing numbers in the equation, what effect does that number in the equation actually have on the graph? We're looking for that relationship. And Jack, what were you about to say?
To the left.
This is how'd you know it was a horizontal shift? Good, that's a good thing. How do you know this is horizontal something?
It's the X.
Yeah, it's inside, it's attached to the x. It's inside the parentheses before this is getting squared. So it's got to be a horizontal something. How do I know it's a shift? Versus a stretch or a shrink, or what's the giveaway that this is a shift? You're adding. Okay? Adding or subtracting are always shifts. And remember, because it's horizontal, it's the opposite direction. So Jack is right, that we're taking this graph and we're going to shift it 4 to the left. So that point right here, the origin, we're now going to go 4 spots to the left. There's the new vertex. There's nothing else going on there, and therefore the whole rest of the parabola goes with it. Okay? And now we can sketch the rest in. There's our new graph. There's what g of x looks like. Okay? No other point changes. There's no change in the shape or anything. So now if we take a look, now let's go to h of x. And again, notice it's x squared, but now we've got a plus 3. What does the plus 3 do to the graph? It's going to go up 3. Why do we know that it's vertical? Because it's not attached to the x. It's not grouped with the x. It's after x is getting squared. Okay? It's kind of attached to the end of the x squared. So I know it's vertical because of that, and same reasoning, it's a shift because we're adding. So we'll take our original parent function, the black one here, and it just gets shifted up 3 units. So that point goes up 3. There's the new vertex, and then once again from there, you can kind of just sketch the graph in. Okay? That's the only point you need to label on your graph. So it doesn't matter whether it's on graph paper. It doesn't matter whether it's in your notebook. I don't really care whether you sketch it. The one thing I will tell you is when we get to the ones that are wider versus narrower, okay, I'm not going to have you plot points to show that it's wider or narrow, but just make sure it's obvious, okay? Because when it gets to the test, if I have to guess, I'm going to mark it wrong, okay? I don't leave it up to a guess. If it's definitely supposed to be wider, make it wider. Make it obvious. Okay, you can still sketch it. If it's definitely supposed to be narrower, make it obvious that it's supposed to be narrower. Okay, just so that you can see it. For example, let's take a look at number 2. Again, we're starting with the same parent function, y equals x squared. We're working with a parabola. And so now if we go to g of x, the question I have for you with g of x is the 1/3 that's there a horizontal or a vertical movement or a transformation? Horizontal or vertical? Let's start there. What do you think? What do you think, Kaylee? Horizontal. How do you know it's horizontal? It's attached to the x. And therefore, it's got to have some sort of horizontal effect. What effect does the 1/3 have on the graph? Okay, we're multiplying in this case, so I know that it's either a stretch or a shrink. Okay, whenever you multiply, so this is going to be a horizontal. If you take a look, let me go back to the notes for a second. If you take a look, whenever c is between 0 and 1, it's a horizontal shrink, and therefore it's a wider parabola. Okay? So if we go back to that, notice, do I have any shifts, by the way? Am I moving my origin? No, that one's not going anywhere. We're not shifting it up, down, left, right, any of that stuff. It's just a wider parabola. So I'm going to put that same point there, and I told you to kind of make it obvious, just sketch it in. There we go. I don't know if that's exactly what it looks like, but at least that's a general sketch of what's happening. Last one, what's the only difference for h of x? It's going to be narrower, okay? Because now, still a horizontal, in this case, stretch, okay? But it's now going to be narrower instead because of it being bigger than 1. Again, vertex does not move. Therefore, there would be an example of what that might look like. Okay, kind of a sketch, yeah.
How would we label them, like, if we're not using any colors and stuff?
Just as f of x, g of x, h of x.
Oh, where would you?
I would put, so like for this one, I would just say right here, I would just put it as, call that g of x. Just put it right next to it wherever you can. Okay.
We have to label on the test.
On the test, you're going to be given, you won't have like here where I give you 3 of them, you'll be given an equation that says sketch a graph. You know what I mean? So you won't have to worry about labeling. You will need to label, like I said, the 1 point, but you won't have to worry about labeling like f of x, g of x, h of x, that kind of stuff. Okay? It'll be, here's a problem. Sketch the graph based on what you know. Okay? Let's keep going. Let's do a couple more. Now we go to absolute value. What does the graph look like for the parent function absolute value? It's a v. Yep. So, origin is where the vertex is at. There's your parent function. There's the absolute value of x. It's over on the wall. Okay. G of x. What's going on here? What's the transformation that's happening for g of x? Yep, moves up. Vertical because the plus 2 is outside of the absolute value. It's not grouped with the x, so it's got to be vertical. And it's a shift because we're adding 2 rather than multiplying. Okay, so we're going to take that. All you have to do is move it up 2. So, up 2 units. There's the new vertex, and now I can sketch in the same basic graph. Okay, that's the only transformation going on there. How about h of x? Now, if you notice, there's 2 things going on. We've got a negative in front, and we've got a plus 4 on the inside. Let's just do one at a time. What's the negative do? It's a vertical reflection. Vertical because it's outside of the absolute value, and negatives always deal with reflection. Okay, so instead, this absolute value now is going to open down instead of up. What's the plus 4 going to do? Horizontal shift, it's attached to the x, but horizontal is always the opposite direction. So we're going to go left 4. There's the new origin. Okay, there's the 1 point I was talking about. And the reflection, instead of opening up, now it opens down. And there's your new graph. Okay? I got one more for you, at least to kind of work through, and then we're just going to identify a few things quick. All right, last example. I wanted to make sure we did a square root one because you haven't dealt a lot with square roots. And so I wanted to make sure that you at least could sketch the quick graph of the square root function. And then when we get down to g of x, if you notice, there's actually 3 different things going on there. So first off, parent function of a square root starts at the origin. That's the starting point for a square root function. And then from there, it's that little kind of curve as it grows a little bit, something along those lines. Okay, h of x, what happens to the graph? What's going on? The plus 2 is under the square root, so it's attached to the x, so it's horizontal. Adding 2, so that's a shift in the opposite direction. Okay? So we take this point, we're going to go 2 to the left, and then again, there's nothing else happening, so we just sketch the rest of that graph in. Okay? Something along those lines. And then finally, g of x. We kind of have a lot of stuff going on here. First, let's just start at the beginning. What's the negative do? Right? Flip it, yeah. It's a vertical reflection. So instead of increasing from your starting point, it's going to get reflected over the axis, and instead it's going to decrease from that starting point. Okay? So we have a vertical reflection. What's the plus 1 do? Goes to the left 1 and up 3. So the shifts are what move your starting point. Okay? So we're going to go left 1 and up 3. So here's the new starting point right there from the origin. And now the reflection, instead of increasing from that point, it's going to decrease from that point. Okay. Still the same curve, it just is reflected. How we doing? Like I told you before, a lot of information on those first 2 or 3 slides about here's what you do in this scenario, here's what you do there, but this is how we're going to be using it. You're just trying to understand what are the numbers in an equation, what effect does it have on a graph. Okay. Last questions I have for you. I'm not going to sketch anything. I just want to go through and just talk through these. Number 1 here, we've got absolute value of negative x. The only difference is the negative. What does that negative do to the graph? This one's a little bit tricky. That's why I want to talk through it. It's a horizontal what? Reflection. Horizontal because it's inside the absolute value. Reflection because we're dealing with negatives. But think about it for a second. If you go through and you have a V and we do a horizontal reflection, what do you get? Same thing. So this graph actually turns out to be the same thing as the absolute value. Because when you're reflected horizontally, it's the same thing in the same spot. Okay? Which is, like I said, one of the reasons I wanted to quickly talk about it. Last one. Let's discuss what's going on here, because there's a lot. Let's work our way through, one at a time. Let's start with the negative. What's that negative do? It's a vertical reflection. Now, and keep in mind, we're dealing with a cubed root now, or excuse me, a cubic function. So normally you've kind of got that increasing from left to right. Because that's negative, it's going to decrease as you go from left to right. Okay? So normally, that is not what I wanted to have happen. Let's go here. So normally this graph would be, would look something like that. Because of that negative, it's actually going to go the opposite direction. It'll look something along those lines. Okay. What does the 2 do to the graph? The negative flipped it from increasing to decreasing. What's the 2 do? Stretch. It's a vertical stretch. Okay, vertical because it's outside of the parentheses. It's not attached to x, and it stretches it. So instead of kind of going just your normal cubic function, it's going to be narrower. Okay, it's going to have a little bit more slope to it, if you will. What's the minus 1 do? Goes to the right 1 and up 3. Okay, so your normal point that's at the origin, you would move right 1, up 3, and then you've got all your reflections and your stretches and all that kind of stuff. So there's 4 different things going on here from that parent function. Okay. How we doing? Questions? Feeling okay? Like I said, today is the lesson. Here's the refresher and the going through things. Tomorrow's plan will be, let's go over any questions. Okay, see where you're at after today. And then I have, like I said, I've got your next homework assignment that will just be an in-class practice day, where you're just doing a whole bunch of these things just over and over and over again to make sure that you get it. Okay? And the hope is, before you leave, you've got your assignments done, you don't have to worry about anything, and they're all turned in and go from there. Okay? Here is the assignment for today. For this section, page 49 of your book. 21 to 55 odd, but skip 39 and 41.